This is the second video on how to solve a linear non-homogeneous case of a first-order differential equation. In this video, I'll cover the second method covered by Greenberg in chapter 2.2 called variation of parameters. After viewing this video and working on the problems, you'll know how to recognize a first-order linear non-homogeneous ODE, and you'll remember how to apply the method of variation of parameters to arrive at a solution. So the topic again is variation, or the method is variation of parameters. And again, we're going to apply it to solve the first-order linear case, first-order non-homogeneous case. And just to summarize, what you're going to do is from the solution to the homogeneous equation, and again, I'm going to refer to that solution as y sub h. It's the solution to the homogeneous equation, meaning it's the solution to the case in which the right-hand side is equal to 0. Remember, that was equal to a e raised to the power of the minus the integral of p of x dx. So that was the solution to the homogeneous equation. And from there, you're going to allow the parameter a to vary with x. Hence the title, variation of parameters. So you're going to you're going to set y is equal to a, which is now a function of x, times e to the minus integral of p of x dx. So that's a pretty simple procedure, well, a simple two-step procedure, and the second step is followed by substituting this into the ODE and solving for y. So this is a simple two-step procedure. Hopefully it's simple enough for you to remember how to apply it. Okay, so now let's get into details of how to do the second step. So the first thing, so again, we have to so our equation is y prime plus p of x times y is equal to q of x. And if y is equal to a of x times this exponent, then the first term, we have to take the derivative of this. And that's going to involve taking the derivative of an exponent. And so let's go back and remind ourselves about the fundamental theorem of calculus, or from the fundamental theorem. So this tells us that if we have some function capital F equaling the integral of little f dx, and little f is continuous over the interval of interest, then we know that the derivative of capital F dx is equal to this function. Or in other words, if f of x is equal to the integral of minus p of x, which is relevant to our problem here, this integral is minus p dx. So I'll just bring the minus into the integrand here, then we know that the f dx is equal to minus p of x. Okay, so let's just keep this in mind as we go through and apply this this equation into the original ODE. So to take the derivative of this, first we have to take the derivative of a. So we have, so y prime becomes the derivative of a prime, times e to the minus integral of p dx. And then we have to multiply a times the derivative of this. So the derivative of this is just our original, we get our original exponent back. And then we have to take the derivative of the term in the exponent, which is the derivative of minus the integral of p dx. And the derivative of the integral of p dx is just minus p of x. And so that's our derivative of y. And then we add the other terms, which is p of x times y, which is a of x, e to the minus integral of p dx. And that is all equal to the right-hand side, and that's q of x. So you'll notice that we have y, a e to the minus the integral of p dx times minus p of x, and then we have y times positive p of x. So these two terms cancel each other out. And so what we're left with is a prime is equal to, I'm going to bring this term to the right-hand side by multiplying both sides by e to the positive p integral of p dx. So we have e to the positive integral of p dx times q of x. So let me switch to the next page. So the left-hand side again was a prime, and that's dA dx, and that's equal to e to the integral of p dx times q of x. So now to solve for a, we can just integrate. We can integrate. So this gives us a is equal to the integral of e raised to the integral p dx times q of x plus c. So this is our solution for a. Now to get y, we just substitute back into our original equation. Y is equal to a times this exponent, and that gives y equals e to the minus integral of p dx. Again, that came from the homogeneous solution, times a, which is the integral of e raised to the integral p dx. This is integral q of x dx plus c. And I need to include a dx in the integral above. And again, this term was a. Okay, so this is the general solution. For the non-homogeneous case. And if you look back at your notes from when we solved the ODE using the integrating factor method, you'll see that it's the same solution. So I've shown you two methods to arrive at the same solution. Now the other aspect about this equation I'd like to point out is that this term, right, gives the term of c e to the minus integral p dx, which is a constant times this function. And you should recognize this is the solution to the homogeneous case. So this gives y sub h, and results in the right-hand side equaling 0. It's this term gives the non-zero right-hand side. And let's call that part of y. It's the non-homogeneous part of y, I guess. Let's call that y n h. So we can describe y as the sum of two terms. The first part that gives the non-zero right-hand side, the non-zero right-hand side being q of x, okay, plus the term that gives 0 on the right-hand side, the homogeneous case. And so when we combine the two, we get, again, 0 on the right-hand side plus q on the right-hand side. Okay, so that's an overview of the general solution using the variation of parameters method, and a little bit more into the two parts of this general solution. Now let's look at an example. And we'll use the same example as I used when we applied the method of the integrating factor method, and that was y prime is equal to 3y. Sorry, y prime plus 3y is equal to x, and here p of x is equal to 3, and q of x is equal to x. So the first step is to get the homogeneous solution. That is y sub h. So y sub h prime, we'll substitute y sub h into this equation with the right-hand side equaling 0. So we get y sub h prime plus 3 y sub h is equal to 0. And I'm going to walk through one more time how to get the solution. And so we can put, so we have dy sub h dx is equal to minus 3y sub h, and that gives us 1 over y sub h. On the left-hand side, the differential of y sub h is equal to minus 3 dx. And we can, when we integrate both sides, we get the log of the absolute value of y sub h is equal to minus 3x plus a constant, and that tells us that the y sub h is equal to a e to the minus 3x. So that was the first step, get the homogeneous solution, which was proportional to e raised to the minus, e raised to the minus 3x power. So the second step was to allow a to vary. So y is equal to a of x e to the minus 3x. And then when we substitute that into our original ODE, we highlight that to keep that in mind. So when we have to take the derivative of this, so using the product rule, we get y prime e to the minus 3x plus a times the derivative of e to the minus 3x power, and that gives minus 3 times e to the minus 3x. And that again was y prime. And then we add to that 3y and equate that with the right hand side. That's equal to x. Oh, actually, let me write out y here. We don't need that intermediate step. So y again was a e to the minus 3x, and the right hand side was just x. And so again, the second term in the derivative cancels with the second term on the left hand side of our original ODE, and we get a prime is equal to e to the 3x times x, right? So we have a prime e to the minus 3x is equal to x. Multiply both sides by e to the positive 3x, and we get this equation. And this gives us, so we have dA dx is equal to e to the 3x times x. Multiply both sides by dx and integrate, and we get a equals the integral of x e to the 3x dx.
So which integration method shall we use to solve this? And I'd like you to stop the video now and see if you can figure this out, maybe even get a good start on the integration. Okay, so assuming you've figured out which method you want to try, I'll go ahead and walk through my reasoning. So first of all, trig substitution won't work because we don't see any trigonometric functions or functions that can be converted easily to trigonometric functions. U substitution works if there's a function here. If you take the derivative, it's part of the integrand, and that's not going to help in this case. And so let's try integration by parts. So integration by parts works if we can take a derivative of part of the integrand, and if we can integrate another part. So let's try, for example, if we set f of x equal to x, for example, and g prime of x equal to e to the 3x, then we can see that we can easily integrate this to get g of x, and we can easily take the derivative of this function, and that just gives 1. So right, integration by parts means that the integral of f of x g prime of x dx is equal to f of x g of x minus the integral of g of x f prime of x dx. And so we have these different parts. So we have f prime of x, and we have g of x, and of course we have f of x and g prime of x. And so this gives f of x, which is just x, times g of x, which is 1/3 e to the 3x, and that's equal to the integral of g of x, which is 1/3 e to the 3x, times f prime of x, which is just 1. And so we know that this integral is equal to the sum of these two terms. And so we now have a integration that's easier. We can evaluate that directly, and this gives 1/9 e to the 3x, and carrying this down gives us 1/3 x e to the 3x. So we have our solution for A, and it's complete if we add our constant. And so substituting A into our equation for y, we see that y is equal to A of x, which is x over 3 e to the 3x, minus 1/9 e to the 3x plus c times e to the minus 3x. And that gives, so this term cancels with these two terms because we have a negative exponent multiplied by e to the positive 3x. And so that just gives x over 3 minus 1/9 plus c e to the minus 3x. And this gives our full solution. Again, this is our non-homogeneous solution, the part that satisfies the non-zero right-hand side. And you'll recognize, hopefully, that this was our original homogeneous solution, right? A constant, in this case, I wrote it as c times e to the minus 3x, whereas the constant that we used before was a. And so this is our full solution.
So let's just continue through with one case in which the initial condition y evaluate at 0, x is equal to 0, is say equal to, say 10, okay? So writing out the general solution, we have y is equal to x over 3 minus 1/9 plus c e to the minus 3x. Since we have a specified initial condition, then we can find the particular solution in which we can define c. This is the particular solution. For the specified initial condition. So to solve for that particular solution, again, we substitute 0 in for x and 10 in for y, and we get 10 is equal to 0 minus 1/9 plus c, and e raised to the 0 power is just 1. E to the minus 3 times 0, and that's equal to 1. And then solving for c, we get c is equal to 10 plus 1/9, 10 and 1/9, and that's equal to 91 over 9. So our particular solution for this initial condition is y is equal to x over 3 minus 1/9 plus 91 over 9 e to the minus 3x. And that is an overview of how to apply the method of variation of parameters to solve the linear non-homogeneous first-order differential equation.